Ever heard that saying, bigger is better? Well, it turns out that when it comes to building smarter AIs, that may not always be true.
Not
Right.
always.
It's easy to think that to make AI more powerful, we just keep feeding them more and more data.
Just kind of stuff them full of information.
But some fascinating new research is showing that for certain AI skills, it might actually be the size of the model.
Like its brain, so to speak.
That makes a bigger difference. And that's exactly what we're going to be diving into today. If you find this kind of stuff as fascinating as we do, hit that subscribe button below and help us keep exploring the world of AI. So
Yeah.
today we're really getting to the bottom of a really big question in AI.
Yeah, very fundamental question.
As we scale these models do, different abilities have different ideal ways to grow. Like, is recalling facts different than my eye?
Right. Different from figuring out a complex problem.
And this isn't just for like the hardcore tech people.
No.
This is something that, anybody who's interested in AI or business trying to use AI,
We're just thinking about the future.
we need to understand this stuff. So we're not just throwing resources around.
Yeah.
It's about efficiency and making sure that, we're building the AI we need
In the best way possible.
in the best way possible.
Right.
So to get to the bottom of that, we're going to be looking at this paper today called Compute Optimal Scaling of Skills, Knowledge versus Reasoning.
It is quite a deep dive.
It is a deep dive.
Lots of data, lots of experiments. They're really looking at how different skills improve
Yeah.
as we tweak the training and the size of the model.
So really what we're going to try and do today is take this paper and distill the essence of it into something
Right, something digestible.
that's useful and makes sense to people
Yeah.
so that you can walk away understanding, these really complex dynamics
Without needing a PhD.
without needing a PhD. Okay, so let's jump in. This whole idea of compute optima, what are they talking about when they say that?
Right, so you can almost think about it like cooking. You need the right balance of ingredients to get the perfect dish.
Yeah.
Too much salt.
Too much salt, not enough sugar.
Too much flour. Right. So it's about finding that sweet spot. And in AI training, the ingredients are really the data you feed it and the size of the model.
Yeah.
So compute optima is about finding the ideal combination of those two given your budget of computing power.
Okay.
So it's not just about raw power. It's about
Using it smartly.
use it intelligently.
Okay. I saw that they mentioned this idea of isoflop curves.
Right.
Can you explain what that is?
Yeah. So imagine you have a set budget for buying ingredients. So an isoflop curve is basically showing all the different combinations of, let's say, flour and sugar you could buy with that budget.
Okay.
And in the AI world, that translates to all the different ways you could combine data and model size while still staying within your computational limits.
Okay.
So by looking at how these different combinations perform, you can start to pinpoint which one gives you the biggest bang for your buck.
I like that. The biggest bang for your buck.
For your computing budget.
Okay, cool. So instead of just looking at like general AI performance, they focused on very specific skills. What were they?
Right. They focused on two main categories, knowledge-based skills and reasoning-based skills. For knowledge, they looked at question answering, basically seeing how Watt and the model could answer questions based on factual information.
Like a trivia game.
Yeah, kind of like a trivia game. They used several data sets with lots of different questions and formats.
Okay.
And the goal was to assess their ability to recall and utilize the information they've been trained on.
Gotcha. And then for reasoning.
Reasoning is a little bit trickier to assess. So for that, they actually used code generation as a proxy. The idea being that writing code, especially complex code, requires a lot of logical thinking, problem solving. You have to follow strict rules.
That's a good way to look at it. Yeah.
So by looking at how well the AI could generate different types of code, they could get a sense of its reasoning capabilities.
Okay. So they're testing these models on knowledge and code generation at different sizes with different amounts of training data.
Right.
What did they find? Like, is the ideal way to scale the same for both?
That's the question. And this is where the research gets really interesting. It turns out the ideal scaling strategy really depends on the skill.
Wow.
Knowledge and code generation showed very distinct patterns.
Oh, that's interesting. So what was different about them?
For knowledge-based question, answering the models tended to be what they call capacity hungry, meaning that for a fixed amount of compute, they performed best with larger models.
Larger models.
Especially early on in training. It's like saying you need a bigger library to store more books, even if it isn't full yet.
Okay.
It gives you the space to grow your knowledge.
Makes sense. And for code generation.
It was the opposite. Code generation was data hungry. These models performed best when they were trained on massive amounts of code.
Right.
It's like learning to code yourself. The more code you see and the more variety you're exposed to, the better you get. So more data was the key driver for improvement.
So knowledge wants a bigger brain, code wants more examples.
Exactly.
And this wasn't just like a tiny difference. This was a pretty big gap.
Oh, yeah. The research showed there was a significant difference in where the ideal balance point was for each skill.
Okay. Now here's a thought. Could this difference be because the training data just happened to have more knowledge-related stuff or more code?
That's a great question. It's a natural thing to wonder. Are the models just reflecting the data they've been fed?
Right. Like maybe that's why they're better at one versus the other.
Right. And the researchers actually thought about that too. So they ran experiments where they intentionally varied the mix of knowledge data and code data in the training sets.
Okay.
Just to see if that would explain the different scaling behaviors.
Makes sense. And what did they learn from that?
Unsurprisingly, adding more data related to a specific skill improved performance on that skill. More code data led to better code generation. More knowledge-rich data led to better question answering.
So far, so good. But what about the optimal points? Did those change when they mixed up the data?
Here's where it gets interesting. Yes, the optimal points did shift. For example, when they increased the amount of code generation, actually started to become a little bit more capacity hungry.
More capacity hungry. So even though it started out wanting more data, once it had enough data, it started to want a bigger model too.
Exactly. It's like you've learned so much from all the examples that you need a bigger brain to organize and make sense of it all.
That's fascinating. But they still found that knowledge tasks really preferred bigger models, even when they had similar amounts of data, right?
That's right. Even when they tried to even the playing field in terms of the amount of relevant data knowledge tasks, still consistently benefited more from larger models compared to code generation tasks.
Okay. So it's not just about the amount of data itself. There's something about knowledge that just seems to need more model capacity.
Right.
Do they have any theories as to why that might be?
They do. They suggest that knowledge is inherently harder to compress. It's just so vast and diverse that it might simply require more space, more parameters to represent it effectively.
So it's like you need more shelves in your library to hold all these different books.
Exactly.
So this is not just an academic curiosity. This has like real practical implications for how we should be approaching AI training.
Very true. If different skills scale differently, then a one-size-fits-all approach to training might not be the most efficient strategy.
Right. So what do? Do they try to like force these different optimal points to align?
They did. They experimented with adjusting the data mix to see if they could get knowledge and code generation to have similar optimal model sizes.
Interesting. And were they able to do it?
To a certain extent, yes. They found a point where the optimal points roughly aligned, but it required significantly more code data than knowledge data.
Okay. But does that actually mean they're creating better AI overall?
That's a great question, and that's where things get even more complex. They looked at how these data adjustments impacted overall performance using different validation sets. And what they discovered is that the validation set itself can significantly influence the perceived optimal balance.
Wow.
Different validation sets tended to be more aligned with either knowledge tasks or code generation tasks, even though they were all drawn from the same general pool of data.
So how you measure performance has a big impact on what looks like the best approach.
Exactly. And that's a really crucial takeaway from this research. The choice of validation set is not trivial. It can make a huge difference in your training decisions.
You could be optimizing for the wrong thing, basically.
Exactly. If you're not careful, you could end up with a model that's not actually optimized for the skills you ultimately care about.
Right.
And the researchers found some pretty stark differences. Like in some cases, the estimated optimal model size could vary by almost 50% depending on the data mix, and by over 30% depending on the validation set used.
Wow. That's a huge difference. So you really need to pick the right validation set that reflects the skills you want your AI to have.
Absolutely. And it's important to choose that validation set up front before you start tweaking your data mix based on a potentially misaligned metric.
Okay. So some really important lessons here about how to train these large language models effectively.
Yeah.
But of course, like with all research, there are some limitations to what this study could tell us, right?
Right. It's important to be aware of those. One limitation is that their analysis of the data mix was mostly done on smaller scales. training and testing these models at very large scales is just incredibly computationally expensive.
Right.
And they also acknowledge that it would be ideal to have even larger and more diverse sets of questions and code for evaluation.
Sure.
And the idea about knowledge being harder to compress is still a hypothesis. It needs more investigation.
Yeah.
And finally, they used code as a stand-in for reasoning. Other types of reasoning might scale differently.
Gotcha. So it's a great start, but there's still a lot to learn. To sum it all up, what are the key takeaways? Like, what should we really remember from this deep dive?
Here's what I would say are the most important points. First, different AI skills have different compute optima.
Right.
Knowledge and code generation as a proxy for reasoning, they scale differently. Knowledge likes bigger models. Code likes more data.
Okay.
Second, these differences aren't just because of the data itself. There seems to be something fundamentally different about how these skills learn.
Yeah.
Third, the choice of validation set matters a lot.
Yeah.
A lot.
Yeah.
If it doesn't align with your goals, you could end up making bad training decisions.
Gotcha.
And finally, aligning the optimal scaling of different skills is possible, but it depends heavily on how you're measuring performance.
So it's way more nuanced than just throwing more data and computing power at the problem.
Absolutely.
We need to be smarter about it. We need to understand how these different skills learn and scale.
Exactly.
It really makes you think, doesn't it? If different AI skills have these different learning needs, how is that going to shape how we design AI in the future?
Right.
Will we see specialized AI models that are really good at certain things?
Yeah, like specialized AIs almost.
Yeah.
Right.
I mean, it's definitely something to think about.
A lot to ponder.
Yeah, it's not just about saving money on training costs.
Right.
It's a whole new way of thinking about AI.
Absolutely.
This has been a fascinating conversation. Thank you so much for breaking this down for us.
My pleasure.
I hope everyone listening found this as interesting as I did.
Yeah, me too.
If you did, let us know what you're thinking down in the comments.
Right.
Ask your questions.
Yeah.
Let's keep this conversation going.
Yeah.
And of course, hit that subscribe button so you don't miss our next deep dive into the world of AI.
Absolutely.
Until then, keep thinking deeply.
Keep thinking deeply.
Bye, everyone.